All right. Let's get started, folks. 4.7 part 2. All right, folks, let's get started. So I want to start, today we're going to talk about compositions of trig functions and their inverses. So we want to start, now interesting things happen when we start, we'll talk about doing compositions of trig functions with their own inverses, but interesting things happen when we do a composition of trig functions with the inverses of other trig functions. So we get to do a lot of interesting things today. But I want to start by remembering one of the properties of inverse functions. So if we do the composition of a function and its inverse, what do we get back out? X. We get back out whatever we put in. And if we do it the other direction, in the other order, we still get X back out. So we can make the composition of a function and its inverse, or the inverse in the original function, and it turns out the same. We can do the same thing. This is true for trig functions. Also, as long as, so I'm going to say if we pay attention to the domain restriction of our original function. So when we constructed our inverse functions for our inverse sine, cosine, and tangent, we had to restrict the domain of those functions in order for them to have an inverse. As long as we pay attention to those domain restrictions, we can say the function and its inverse undo each other. But they have to undo each other within those domain restrictions. So what I want to do is go through a few examples to illustrate what we're talking about. So all of these, we're just evaluating these things. So we're going to do A. We want to find the sine of the inverse sine of 0.12. So in the parentheses here, we have the angle whose sine is 0.12. So let me draw a picture there. There's an angle between negative pi over 2 and pi over 2. The 0.12 is pretty small. There's the sine, the y coordinate. There's that angle whose sine is 0.12. That's between negative pi over 2 and pi over 2, that angle. So these two are just going to undo each other. All right, so we're good there. That makes sense. That's how inverse functions have always acted. Let's look at another example. The inverse sine of the sine of 3 pi over 4. Now, it would be a mistake to say that the inverse sine of the sine of 3 pi over 4 is 3 pi over 4. Why? Well, we could do parentheses. That would be okay. Is 3 pi over 4 between negative pi over 2 and pi over 2? No. No. So we need to figure out the angle, because we know that what we get out of an inverse sine function is an angle, we need to figure out the angle between negative pi over 2 and pi over 2 that lets that work. So the way I suggest that you do that is inside out. So I'm going to say this equals the inverse sine of, what is the sine of 3 pi over 4? What is it? Square root of 2 over 2. So that's what we're looking for. And now we want an angle whose sine is square root of 2 over 2, and that angle needs to be between negative pi over 2 and pi over 2. Yes? Pi over 4.
It was all you. It was all you. I realized that. It was all you, and I respect that.
So our angle that we get out of this inverse sine function has to be between negative pi over 2 and pi over 2. All right, so let's look at another one. The inverse cosine of the cosine of 3 pi over 2. Yes?
So I know like regular cosine and sine functions don't have any domain restrictions, but if they do we need to keep in mind domain restrictions for both functions, or just like this?
We need to keep track of the domain restriction for the one where we're working with the inverse, because we restricted the domain of the original function so it had an inverse. So here, for example B, we had to pay attention to what the domain restriction of our sine function was so we could do the inverse sine. Okay? All right, so I'm going to say for this one, we want the inverse cosine of the cosine of 3 pi over 2. It would be a mistake to say that this equals 3 pi over 2. Why?
It's not.
Not between
0 and pi over 2.
0 and pi for cosine. So let's do this one inside out.
That equals cosine of
Negative
negative 0.
0?
0. 0. I was
0.
Again.
And what is the inverse cosine of 0? What's the angle
Pi
between
over 2.
0 and pi with a cosine of 0? Pi over 2. All right, questions? Okay, let's look at another one. We want the inverse tangent of the tangent of 5 pi over 6. Is it 5 pi over 6? No, because it's not between negative pi over 2 and pi over 2. So let's do this one inside out. Inverse tangent, what's the tangent of 5 pi over 6?
3 over 3. 3 over 3 over 3.
And we're at 5 pi over 6. So sine is positive and cosine is negative.
Negative square root of 3.
Negative square root of 3 over 3. So now we need an angle between negative pi over 2 and pi over 2 that has a tangent of negative square root of 3.
Pi over 6.
We want it to be negative?
Negative pi over 6.
Negative pi over 6. So we are here. There's 5 pi over 6. There's where our tangent was negative square root of 3 over 3. So the angle between negative pi over 2 and pi over 2 that has the same negative square root of 3 over 3 tangent is this angle. All right, let me see if I can trick everyone now. The cosine of the arc cosine of 6 is it 6? What is it?
Not possible.
Not possible. Why? It's more than 1. What? There's no angle that has a cosine of 6. So this is no solution. Because
More than 1.
the arc cosine, the inverse cosine, is an angle whose cosine is 6. No angle has a cosine of 6. There's no angle with a cosine of 6. All right. So let's do a couple more. How about the inverse sine of the sine of pi? Is it pi?
Yeah.
All right, folks. Let's stop talking. Is the answer to this one pi? No, why?
Like above pi over 2 or something like that.
It's not between negative pi over 2 and pi over 2. So let's do this one inside out. This is the inverse sine. What's the sine of pi?
0.
0. What is the angle between negative pi over 2 and pi over 2 that has a sine of 0?
0.
0. The inverse sine of the sine of pi is 0. Where were we at before with our letters? E, so that's F. How about the cosine of the inverse cosine of the square root of 2 over 2? All right, is this one going to give us any kind of problems?
No. It's not going to give us.
If we're not sure, we can always do it inside out. Cosine of, what's the inverse cosine of square root of 2 over 2? What angle gives us a pi over 4? And what's the cosine of pi over 4? Square root of 2 over 2. So this one, because we have a nice angle that's within our domain restrictions of our cosine function, they undo each other. All right. I'm going to turn this one around. I'm going to say the sine of the inverse sine of pi. How about that one?
Pi. Well,
Is it pi?
pi is larger than 1.
Pi is larger than 1, so there's no solution. No angle has a sine of pi.
Wait, Mr. Beaver.
Mhm.
So it has to be between pi halves and pi.
Negative pi over 2 and pi over 2 for sine.
And then for cosine, what is it?
0 and pi.
Oh, okay.
All right, last one. F, G, H, I. Inverse sine. All right, folks, stay with me. Inverse sine of the sine of 7 pi over 6. Is it 7 pi over 6?
Oh, it's 1 over
No?
2. Inverse sine of 1 over 2. Negative 1 over 2. 1 over 2 is 1 over 2.
So let's do this. Inverse sine, the sine of 7 pi over 6, what is it? Here's 6 pi over 6, 7 pi over 6. Negative 1/2. So what is the inverse sine of negative 1/2? Angle between negative pi over 2 and pi over 2 that has a sine of negative 1/2? Negative pi over 6. So for this one, we started off here, and we ended up going over here for our answer. All right. Questions there? Well, things get more interesting when we start doing compositions of trig functions with the inverses of other trig functions. So let's do that. Let's make it more interesting. Let's find the exact value of the cosine of the inverse sine of 3/5. So exact value is a hint that this isn't something that you're going to plug into your calculator. Well, let's think about this for a second. What is this? How can we rephrase this? How have we been thinking about the inverse trig functions? The angle. Whose sine is 3/5. That's what the inverse sine of 3/5 is. The angle whose sine is 3/5. Let's call it theta. Well, we can draw a picture of that, can't we? There's the angle whose sine is 3/5. Well, what can we do here? We can do the Pythagorean theorem. So how long is this side? 4. Well, this is asking for the cosine of that angle. Cosine of that angle is 4/5. So we can say the cosine of the inverse sine of 3/5 is 4/5. Isn't that nice? As you move forward, this thing with the triangle, the sides, these being the sides of the triangle, that's going to be more how you will use this kind of information in the future. All right, let's look at another one. Questions here? This is my favorite kind of problem from the entire chapter. But we'll do one more type of example after this. We want to find the exact value of the sine of the inverse tangent of -1/2. This is the angle whose tangent is -1/2. Let's call it theta again. Whoops. Why did I draw my triangle that way? It's negative. It has to be in the fourth quadrant. So this is -1, and that's 2. We can find this hypotenuse. It's going to be the square root of 5. 2 squared plus 1 squared. Well, the sine of that angle is -1 over the square root of 5. And it makes sense that the sine is negative because we're down in the fourth quadrant. Our y coordinate is negative in the fourth quadrant. All right. Nice kind of problem. Let's make it even more interesting.
Already interesting.
I know you thought it couldn't. It's not possible. It's definitely possible. So the way they'll ask this kind of question is it will say something like, write the sine of the inverse cosine of x as an algebraic expression in x. This is really the same kind of problem, but instead of with numbers, we have a variable here. This is the angle whose cosine is x. Let's call that angle theta. There's that angle whose cosine is x. We want the sine of that angle. So we need to find this side of the triangle using the Pythagorean theorem. Can we see what it's going to be? If you didn't see that right away, you can call this a. So we have x squared plus a squared equals 1. So a squared equals 1 minus x squared. So a is the square root of 1 minus x squared using the Pythagorean theorem. We want the sine of that angle. Square root of 1 minus x squared over 1. So there's my answer. The sine of the inverse cosine of x is square root of 1 minus x squared. So with variables, this is how you'll see this type of idea applied in the future. But in the future, in calculus, you actually go from this expression back to the sines and cosines. So you kind of go in reverse. It's called trig substitution. And it's really fun. You probably thought this couldn't get more interesting, and it does. Yes. So what I was just explaining in calculus, there's a thing that you do called integration, where you're adding things together. You want to add a bunch of stuff together. So you want to find the area of something. You want to find what the total distance that something's traveled if it's going at some variable rate of speed. So you have why?
So like one job, like let's say like
An engineer, rocket scientist.
So if we, since we don't want to become those, can we just not hightail out of here?
The thing is, you never know. You never know what's going to happen.
pretty sure I'm not going to.
No, well, here, listen. Hang on. I'll take a small tangent. My wife went to film school. She has a degree in fine arts. My wife is now a database programmer.
What?
Yes. She never in a million years thought that she would ever do anything other than art. And now she's a database programmer. And she's pretty good at it. So you never know what's going to happen. All right. Same thing as last time. We want the tangent of the arc cosine of 2x. All right. Stay with me, folks. We're going to do this the same way. This is the angle whose cosine is 2x. So let's call it theta. We'll draw a picture of that angle. There's theta. The cosine is 2x. We'll find this side of the triangle. So this is 1 minus 4x squared. If we call that a, we have a squared plus 2x squared equals 1. So a squared equals 1 minus 4x squared. A equals the square root of 1 minus 4x squared. We want the tangent of that angle. So the tangent of theta is the square root of 1 minus 4x squared over 2x. And the way you'll see this in the future when you do this in calculus is you will go from this expression, draw the triangle, and rewrite that as tangent theta. That would be cosine, and then you work with the trig functions rather than working with this really ugly square root of 1 minus 4x squared stuff. So we call that trig substitution. Yeah. Yes. All right, questions? And the other thing that might happen is in the future, you might decide, Caleb and Kaylee, you might decide that this stuff is actually interesting and you just might do it for fun.
I mean, I feel like it's interesting and I understand it, but like as of right now, we don't.
What's that? Yes. Have you ever heard that the song by Weird Al Yankovic, White and Nerdy?
Yeah.
Yeah, he talks about doing vector calculus for fun. No, I left it at home today. So what I'm doing with that is I have to do an oral exam for my master's degree. So I'm doing a presentation on some of that material. No. It's a totally different thing.